Now, I don't happen to have one here, but at campus, what we have is a little spring gun. Okay. And so what happens is has a rectangular case, and then you compress a spring, and there are little notches to keep it held in the compressed positions. You then can load it with a little, chrome-plated steel sphere. And then when you release the spring, it shoots the little sphere up into the air. So I usually call it a spring gun. Okay. And so what we're going to do is we're going to go in, and I'm going to have the spring compressed, and then we're going to put the ball on top of the spring in the compressed position. And then we're going to release it, and it's going to shoot up into the air. It all moves in here, but I'm going to move them over like this so that I'm not drawing on top of myself. Okay, so, and at this stage, we're going to launch the ball up into the air. So this would be the launch speed, or they probably might call it, if they're going to go with the gun analogy, then they're going to go with like the muzzle velocity or the muzzle speed. And then the ball is going to continue on up until we reach this kind of highest position. And so this, oops, I drew through the ball. This is going to be our equilibrium position. Okay, of the spring. And so then what we're going to have is that we're going to have compressed the spring by some amount here. So this is my displacement from equilibrium. And I don't know, let's go in and say that we're going to compress it by, 15 centimeters or something like that. Okay. And then let's go in and say that the mass of the chrome-plated steel sphere, the mass of the ball. And so this would be the one like what we used in the projectile lab that we rolled down the ramp and then launched into the room. It's the same sphere. I'm pretty sure they're all the same. They're close. All right, so let's say that the mass of the ball is going to be 25 grams. And so then, carefully, we can then mark that as, 0.025 kilograms, because we're going to want everything in SI units. And then we're going to go in, I'm going to state what the spring constant of the spring is going to be. So this is how stiff or how loose the spring will be. And so I don't know, I'm going to pick 125 newtons per meter. This is the point where I don't really have a good feeling for it. And if I pick poorly, then, we'll put the ball into, launch it into like low Earth orbit or break the speed of sound as it launches off the spring. So, hopefully it won't do things ridiculous like that, but we're going to go with these numbers and see how we do. Okay, so I just want to pick something to practice our, our calculation. Okay. All right. And so the questions will be, how fast is the ball going to go when it launches up off the spring? And then we'll ask, a question like, well, how high did it travel? And as per usual, the how high did it go? Sorry, my shoulder caught. As per usual, how high does it go is not really a well-posed question. It's like, well, how high above where do we want? I'm going to draw it as how high above the original, this equilibrium position. But the question could readily ask how high above this initial compressed location. And so you just need to be careful with how they word things. And you just read the question, so. All right, so then what we're going to do is we're going to go in. I have 3 locations of interest. We're looking at the spring and the ball. And so I'm going to label these as, A, B, and C. And we're going to write down our mechanical energy at each of these locations. And then we're going to figure out how to, solve. So the first term here is the kinetic energy. So you ask, is it moving? And so what we're going to analyze, we're going to analyze the ball. And so initially when we have the ball, compressed on the spring, so kind of in the cocked and loaded position, and then we're going to release it and then shoot it up into the air, the velocity at this point is going to be 0. Okay. And so then our initial at an A, so at this point we have no kinetic energy. So the kinetic energy is 0. Okay. And then we get down to the point where we go, great, does it have gravitational potential energy? And the answer to that is, well, that depends upon our coordinate system, which we haven't completely picked yet. Now, remember, we have to make sure that what is true about our coordinate system. What choice did we already make and can't make again, or can't remake? Yep. So up has to be our positive y direction. But what we get to choose is where the 0 is. Now, my personal preference is I kind of like to put the origin of the coordinate system at the equilibrium position. It may not make it the easiest choice for certain questions or certain problems, but what I kind of like is then the compression amount is related to my position, and they're not different. Okay, so I kind of like to make that this is going to be the 0 of my coordinate system. And since we went down by 15 centimeters, then this will be negative 15 centimeters. And if we go up by some height, then this will be y equals like, plus h, where I don't know what that is yet. Okay. And so with this choice in place, then because we are below the origin, we are going to have some negative gravitational potential energy. We're going to put in that this is the mass of the object. Let me write down our mechanical energy term so we can look at it. And again, I always like to write the reminder in here. That up has to be that positive direction for the gravitational potential energy. So we did kinetic energy is it moving? And the answer was, well, no, that's the beginning. Does it have gravitational potential? Well, that depends upon the y coordinate. In our coordinate system, we have to finish picking. And so with my choice being the 0s at the equilibrium position of the spring, then the answer is no, we do indeed have gravitational potential energy. And then the spring potential energy. So this is going to be the mass of the ball. So 0.025 kilograms times g, which is our 9.80 meters per second squared. Do not make it negative. Have I said that enough times? Yep. Don't make it negative. And then the y coordinate will be a negative 15 centimeters, but we're going to need to be an SI unit. So this will be 0.15 meters. So there's our gravitational potential energy. Notice it is negative. I kind of like seeing that because that's an important thing that it can be. Certain choices will make it negative, and that's fine. And again, this is part of the reason why I don't like MGH for the gravitational potential energy, because H's read like heights. Heights are only positive. Okay. And when you look at things like in second semester, when we analyze the hydrogen atom in the Bohr model, then what you'll find is that the potential energy of the electron as it is bound to the proton in the nucleus of your hydrogen atom is negative. And that is important because it is bound. Okay. So, and now we have a spring. The spring is compressed from its equilibrium position by some amount. And so we can put in, this is 1/2 the spring constant. I chose 125. Hopefully that's not too stiff, too big. And now in this case, we can go in and state that this X value for the compression amount, you can make it at negative 0.15. But we are going to square it. And so I want you to be careful with that, because anytime you square a negative, it will become positive. But on your calculators, if you type -2 squared, it will come out -4, because it'll square it first and negate it second, because the negation is a unary operation and the squaring is a binary operation, and it does the binary operations before the unary operations. And so you get, if you type -2 squared, you get -4. So then you need what? Parentheses to force the order of operations to be the way that you want it to be for it to be correct. And then we end up with like possibly lots of nested parentheses. So a lot of times I just drop the minus signs if I'm going to square it because I don't want to mistype things into the calculator. So be careful. But definitely we don't want to miss this negative sign. So this is a negative energy, and then this is a positive energy. And what you should notice is this is a number. On all the other problems we worked, we didn't get any numbers because we had M's and the M's didn't know and we canceled them out and things like that. But when you have a spring and an object, since the spring term doesn't have any mass in it, there's no M's here, then you can't cancel anything out. Therefore, all of a sudden, we now need to know all the masses. So interesting thing to recognize. What's our energy here today? And again, be careful with this minus sign because we're going to square it. I wouldn't write it, but you know, as long as we do it correctly, it doesn't matter. All righty, so 1.37 is the good answer. And I'm going to go with the extra digits, so the 695 for the moment, because we're going to do additional calculations and I want to prevent any round off error. Okay, so there we go. Questions? We got A. We're going to do B and C. Well, at B, the ball is going to be moving, so there will be kinetic energy. Okay, and so we can write down that this is 1/2. The mass of the ball is the 0.025 times our, launch speed squared, or muzzle velocity, or whatever we want to call that. And then we go, great, does it have gravitational potential energy? Well, with our choice of the origin, it does not at position B. So no gravitational potential. And then you go, great, does it have spring potential energy? And the answer is, well, since the spring is at the equilibrium position, it is neither stretched nor compressed by any amount. And so therefore, there's no spring potential. And we can clean this just a little bit. So this is 0.0125 V squared. So let's do C. So at the highest point here, is the ball moving? Does it have kinetic energy? What do y'all think? Both John and Olivia said no, and they are correct. Because if it's moving, you're not at the highest point, right? It goes up, stops, turns around, and comes back down. This is straight up, straight down motion, no parabolic stuff. And so, yeah, up here at the top, if we're going to be at the highest point, then it needs to be no longer moving. So there is no kinetic energy. And then what we'll have is that the gravitational potential energy is yes, but we don't happen to know. So it's the mass of the ball times G times this Y value, which I marked as H. So we could keep it as either Y or H, whichever way you want to do that. Either are fine. 0 to 5. Oh yeah, don't make this negative. And then I'm going to go with plus H if you guys are okay with that. Or we could just leave it as Y. Now, the thing is that once the ball leaves the spring, then the spring's going to come up to the equilibrium and stop. And so then there won't be any, spring potential energy. Now, the thing is that technically it's a little more complicated than this. Okay. So technically what happens is that these potential energies are shared between the objects that are interacting with the conservative force. So this is the gravitational potential energy is related to our gravitational force, which is conservative. And that's the force between the ball and the earth. And the thing is, by shooting the ball up into the air, the Earth's motion does not change. Okay. Did we do that little one when we did the gravitational piece? Some of the times I like have my little person or me jump, and then we talk about how the Earth moves up to meet them as they come back down. Did we do that? Sometimes, yeah, okay. Cool. Yeah, and then what you get, the acceleration is like, 10 to the minus 20 some odd, and then the motion is 10 to the, you go, yeah, it moves up by 10 to the minus 20 something meters. And the atom was 10 to the minus 10. The nucleus is 10 to the minus 15. We're more than 5 orders of magnitude smaller than the nucleus of an atom. Yeah, there you go. Yeah. I mean, it's essentially, there's no motion. And so that's exactly what happens, is that in this situation, the energy is shared between the ball and the earth. And when you read in the chapter, they're going to talk about the ball-earth system. Okay, so they're going to talk about systems throughout this. But because gravity interacts with the earth and the earth really isn't going to do anything, then you don't really need to account for the motion of the earth because it's not going to change. And then when we do the spring potential, it's the spring and the ball. But then what'll happen is they're going to take the spring and they're going to treat it as if it's an ideal spring. Okay. And one of the characteristics of an ideal spring is we treat it as if it is a massless spring. Or if that bothers you, then you can say that the mass of the spring is negligible compared to the mass of the ball, kind of things, is how they usually phrase that. Okay. And part of the reason for that is if we look at the spring as it moves, right? The bottom of the spring isn't going to move at all. The top of the spring moves fully, and in between it moves in between. So one part doesn't move at all. This part moves fully, and in between you move in between the full motion and the no motion. Great. What's the kinetic energy of that? Yeah, not so wonderful. So, but if it's massless, if this m is 0, then I don't need to worry about how do I find the motion of the spring that isn't uniform throughout the spring. And so this is the simplification that is done. And again, this is to make the problems more readily solvable. They may not be quite as realistic, but they at least give you a starting point for estimating, what the true answer would be, just like what's the volume of water in the lake. We can't like measure it directly. It's not like you're going to bucket the water out of the lake to figure out how much water was in there. You're going to have to do estimates. And so there are certain things that we need to make tractable. So, but that they still have value. This was why we had that discussion about the order of magnitude estimates. So at the chapter 1. So, all right. So then the thing is that once we break contact, then we don't worry about the spring anymore. And so then there's no spring potential. So the pictures, you have it come up and stop and the ball goes on. So there is no stretch or compression on the spring. And so it's just this gravitational potential energy. 0.245? I think it is. Each. All right, thank you. All right, now the next thing is, well, what do we do with this? And the thing is if we go back to our little handy dandy steps, there they are. So we have our sketch. We ID'd our, locations of interest, mechanical energy at each location. So we got those parts done. Now we need to worry about any work done by non-conservative forces. And so there's 2 parts to the motion. There's the part where we're going up on the spring and the part where we're moving in the air. I'm just going to draw here and there. I know I usually do in-betweens, but I didn't leave myself any room. Okay, so at this stage, what forces act on the essentially we're looking at the ball, even though we're technically supposed to do the ball, earth, spring system. We're going to essentially neglect the spring and the earth. We're going to make things nice. But for the ball, what forces act? There's gravity. And now the other one you want to be careful with. So what's our other force other than gravity? I mean, it is in contact. There is a surface, but it's in contact with what? Object. Yeah, it's in contact with a spring. And so the thing that matters here is that because we, displace the spring down like that, then my spring force goes in the opposite direction of the displacement. You're like, okay, so what's the big deal with not calling this a normal? And the big deal is in the next step where we go, great, are these conservative or non-conservative forces? And so when you call it gravity, that's conservative. And then what we find is that the spring force is conservative, but a normal force is not. So this is why we have to be careful and make sure we label that as a spring force, okay? Because then it's conservative, and then you're like, oh, I don't have any non-conservative forces. You call it normal. Normals are technically non-conservative forces. This is like calling the acceleration when you move in a circle that you want to call that centripetal or radial, and you do not want to call it like X or Y or something like that. Are we good? Everybody okay? And I don't think we need any static friction per se, because it would be along the surface of contact, and I don't have any horizontal, motions or displacements or anything like that. So are we good? What about when it's in the air? Well, when it's in the air, then we just have gravity, and gravity is conservative. So everybody see why I want us to be careful and that this is not a normal, it has to be a spring because we're in contact with the spring. Because then the spring force is conservative, but a normal force would not be conservative. And then you would have an upward normal, and an upward displacement would do like positive work kind of things. And all of a sudden, everything goes sideways on your problem. So. All right. And so then what we find is that our work done by the non-conservative forces is 0. And this is, because there aren't any. So this was our option number 1 on the list of 3 ways in where we could conserve mechanical energy. So this is the requirement. We have conservation of mechanical energy. We'll set the energy equal to the energy and solve. All right. Now, notice that the energy at A is a value. We know it. And at B, we have the unknown, how fast is it going? And in C, we have the how high kind of thing going on. All right, so let's go in. And so what we'll start off with is we'll set our energy at B equal to the energy at A. And I'm going to do it this way because then my variable's on the left side, which is where I like it to be. Just annoying like that. So 0.0125 V squared equals my 1.3695. And then to solve for V, we would divide both sides by the, the 0.0125. And then to finish, we'll take our square root. I mean, again, we should really pick up the plus and the minus, but it's a magnitude of a vector, so it's only positive. And so what do we get? All right, tell me the bad news. How fast we launch the ball. Hopefully we're not doing highway speeds. Oh, good, good. 10.5 is not highway speeds. We did not break the speed of sound. We're looking pretty good. Though I think it's probably too fast for actually doing like in the lab room kind of things as a little demo experiment, which is usually what I do. So I think that's probably too fast. And we got to be like 5 and under kind of to stay within the room. So, but that's okay. We'll just pretend it's going to be all right. And then, so this is the speed at which we launch the ball into the air. So the launch speed, the muzzle velocity, you know, whatever we're going to do, muzzle speed. And then we can go in and solve for how high did it go. So I can take my energy at C, and we could set it either to A or B because, you know, they're the same. So I'm going to do A because I already know the number. And so then this is our point 2, 4, 5. H equals the 1.3695. And then we'll just divide. Because that's like a quarter. And so that's like multiply by 4. So yeah, I'm getting like 5 something meters. That's not so great. You know, if you're going to be in the room, that's not so great. We're outside because that's like, you know, building height. Yeah, 5.6 meters. Now, again, let me remind you that we would need to reread the question to go, is it how high above the equilibrium position or how high above the initial launch position where it's compressed? Because we might need to add this 15 centimeters on to get the answer, depending upon, you know, which way they want it to be. Okay. So we would just need to read. So this is, I think I mentioned this in chapter 2 when we did like the free fall stuff, that how high is kind of a tricky question. You just have to be careful with it. So, you know, check of where, since we didn't have worded questions and I drew a picture, then this is what it seems to be the correct answer. This is how high above the equilibrium position. But we might need to, like I said, add the 15 centimeters on or something like that. All righty.